Yeah, Fung, thank you for the kind introduction. It's always great to be back in Vancouver. Vancouver is my hometown. I've suffered through 2 Canucks Game 7 defeats, so it's nice to be back, and especially at UBC to to talk about sustainability and green chemistry. And so the talk is ACS GCI Natural Polymers Consortium. So the idea for the next 40 minutes is really just to give all of you a glimpse of what the ACS does, what the Green Chemistry Institute is currently doing with respect to sustainability and green chemistry, and what this new consortium is all about that I think has much alignment with the Bioproducts Institute here at UBC. Just a very quick background. Fung already talked about most of where I'm from. Did my PhD in Toronto. I spent actually 14 years with the feds at the National Research Council in Canada. So more or less starting off as a research associate at the National Bioproducts Program. You see the laser here. And then in 2016, I actually moved over to the program side, so leaving the lab itself to assume a leadership role in the program, working with different stakeholders, North America, actually internationally, with respect to developing technologies that are aligned with sustainability and such. In 2018, I took over the team that actually was part as a postdoc here. So, and then we had that weird time with COVID. So at that point in the government, we actually pivoted from doing our usual research to actually addressing the critical challenges of the pandemic. So I was working a lot on that. And then 2021 to 2024, actually was an adjunct professor at McGill. So I actually did a lot of collaborations and am still are with McGill Chemistry. And then 2023, I moved down to the United States, and I've been with the ACS since then. Really just a quick background of where the science and why maybe I'm here from the research perspective. So I had a collaboration with McGill University. So Audrey Morris, the Department of Chemistry, working with a couple of her grad students. So most of the work here is done by Dr. Tony Jin, who's now in Germany as a postdoc, and also Galen Yang, who's still a PhD student with Audrey, probably in his 4th year at this point. So the core technology that we developed at the NRC was focused on waste valorization. So we actually pivoted from cellulosic feedstocks into marine waste because that's what the government wanted us to do, look into that. So we took the technology and developed different chitin, chitosan nanocrystals from seafood waste. I think the main thing that I will say about this work is the fact that we actually started to look at it from a more sustainable perspective. So the traditional methods were very, solvent dependent, so a lot of water, a lot of heating, and over 16 hours. But Tony was able to develop some mechanochemical processes that were able to actually streamline that process to get the similar materials. So Galen himself actually took the mechanochemistry work and actually started to develop methodologies for actually functionalizing different biopolymers. So he had a couple of papers that came out recently. But really, the exciting part of all this started to happen when we had a collaboration with another part of McGill University. So it's with Jen-Yu Lee at the Mechanical Engineering Department. And so we were interested in actually using these, nanomaterials as, what can you do with them? So let's make some hydrogels and see what happens. And so we developed some, drug delivery systems using the chitosan nanocrystals, which then eventually led to what Jen-Yu was developing actually was this ultrasound method to make a tough bioadhesive. So really using chitosan nanocrystals as an anchoring agent within skin to be able to put a hydrogel patch on, and it actually had very good, physical chemical properties for healing. So, that's the kind of work that kind of summarizes what I've been doing the past 5 years. Still am right now, but now that I'm in America, there's different MO for my work. So a little bit about the ACS. So what do people know about the ACS? Just a show of heads.
It's a fantastic organization with lots of different divisions, and so including cellulose and renewable materials division, and then also polymer science division, and also polymeric materials science and engineering division that all relate to what we do here in the Bioproducts Institute.
Yeah. So I think most people know ACS through 2 things: the publications and the conferences. So we are essentially a nonprofit that was founded in 1876, chartered by the U.S. Congress. It is one of the largest scientific organizations in the world, as Fung had pointed out. And this is our mission and vision statement. We're about 5 blocks away from the White House, so there's a new guy that's returning to that place very soon. But essentially, what I want to say is the fact that the ACS is more than publications and conferences. We do have a lot of grants. So the PRF grant is one of them. I run a sustainability grant, which I'll briefly talk about today. But we also have chemical abstract services. So that's a division that's actually located in Columbus, Ohio, that handles a lot of our data services to our different clientele. And at the bottom, we do have 2 national meetings each year, one in the spring and one in the fall. So the spring one coming up in 2025 is in San Diego. So if you want to go to the beach, that's pretty nice. Or if you want to visit DC, it's going to be in our headquarter town of Washington, DC in August. So part of the ACS is actually the Green Chemistry Institute. So this is part of our division of scientific advancement. This was actually part of the ACS since the turn of the millennium. And our mission really is to catalyze green chemistry and sustainability throughout the entire enterprise. So whether it's in academia, in industry, government, we want to actually promote sustainability in green chemistry as such. And to do that, we do have 4 strategic goals. And some of these strategic goals are very much intertwined with what I'm going to talk about today. The first one being science. So this is kind of where I focus on scholarships and grants and awards. So there's plenty of money available for students and postdocs here to apply for. So check out our website, and you can actually apply for those kind of things. On the education side, we do have teaching modules that are available to educators to really help, bring sustainability and green chemistry to the classroom. And at the same time, for the grad students and the postdocs, we do have our annual summer school that for next year will be at the University of Vermont. I know that there's someone from UBC that attended the summer school this year, so from what I gathered, they enjoyed it. So actually, please check it out. Applications have already started for this cycle. For today, at the industry part, I'm going to talk more about that. And then equity. I think this is an important aspect that needs to be discussed a lot more. So looking at environmental justice issues and whether or not sustainability and green chemistry can be a solution to some of the problems that are affecting, disproportionate communities and such. So this is the GCI team. There's 7 of us. What I'll just quickly say is that for today's part of the consortium, it's really led by Dr. Izamir Martinez. So she's the Assistant Director of Industry. And so I just work with her because I know a little bit about biopolymers. So what is green chemistry and why? So how many people here are familiar with this textbook? 3 people. So anyway, this is something that was written by Paul Nassis and John Warner more than 20 plus years ago. It essentially is looking at, what can green chemistry do to design and chemical products or processes that reduce and eliminate the generation of hazardous substances. I think today that definition of green chemistry is really advanced to the point where we have to also think about systems thinking and how one thing in chemistry may affect another. So for example, when you think of nitrogen chemistry, it's great because we need nitrogen to make fertilizers. So fertilizers will help grow food, which helps us, feed ourselves. However, at the same time, with nitrogen chemistry, you can make weapons. So that's something that has to be thought about when you think about in terms of systems thinking. However, with green chemistry, one of the things that is important is that it does provide opportunities for, improved efficiencies in chemical processes. But what I really want to focus on is really those 2 items in here, which is, increasing the exploration opportunities for innovation. And that's why the consortium that I'm going to talk about today is really focused on that. How do we develop new materials that are good for us, good for economically, and how do we actually get to that point? So in 2004, this organization, OECD, came up with a larger definition of what we call sustainable chemistry. I won't even read this, but I want to say that this first part is probably what is about green chemistry, and the rest of it really is about the social and economic challenges that are required to be overcome to actually say that, okay, we have something that can be useful and safe for, folks like us as consumers. And so really, the definition of sustainable chemistry is still in flux even to this today, because there's really no single sentence or way to really define it where we can just say what green chemistry was on the slide earlier. And the reason why I bring this up is because if we don't have a true definition of sustainable chemistry as a group, it's really hard to actually define what are those parameters as to what that is. And so one of the consequences of that is, greenwashing. So, making something to appear more environmentally friendly or less environmentally damaged than it really is. So there's numerous examples out there. An example of greenwashing is like you have your water bottle, but has like a little tree on the packaging, right? That's greenwashing. Or if a company decides to actually amplify one part of their process or their product and say, oh, this is environmentally friendly, but the rest of it is like completely damaging the environment or emitting significant amounts of carbon, then that's also an example of greenwashing. So that's something that we need to be cognizant of. But on top of that, without true definitions of sustainable chemistry, we can actually look at regrettable substitutions, which is actually becoming a far more increasingly damaging problem. Because as we try to substitute different products that were once we thought to be toxic with something that's even worse, it actually makes it 10 times worse because now we have to remediate two different things. So, these are some of the examples that you see here. BPA, I think everyone's familiar with that one. But, methylene chloride is currently in the crosshairs right now. So I don't know how many people here use DCM in their lab work. Wow, good crowd. But if you talk to an organic chemist, they're already like thinking, how on earth are we going to do chromatography or chemical reactions without DCM? That's been kind of one of the standard solvents that everyone uses. So these are the kind of things that we need to think about. And there's a lot of reasons why regrettable substitutions happen. For example, there's a lack of data of what we're actually trying to produce. There's a lack of information on what happens when we produce the materials that then lead to the end of life. And so, these are the kind of things that this new consortium is actually thinking about. So I'm really setting the tone for how we want to have this discussion today. So in 2023, we had this group, Change Chemistry, and also UMass Lowell and Beyond Benign. They came up with a more, shrunk down version of sustainable chemistry, and that's kind of in the middle here. But what I want to focus on is the fact that this definition that they came up with for sustainable chemistry really takes into account things like data transparency, so where you're getting your materials, is it sourced properly? When you make the materials, is it really hazardous, or to yourself when you're in the laboratory? Circularity of the materials. When you actually are done with the materials, can you actually be able to reuse them in some form as opposed to being tossed in the garbage or in the landfill or in the ocean? And then once it actually gets out into the ocean or in the environment, what is the environmental impact of those materials to the community, which leads to this equity and justice part that I briefly mentioned earlier. I think, being in Canada, I want to, sprinkle a bit of Canadian content throughout the talk today. And I think, everyone familiar with what's happening in Sarnia right now? And this is actually what's happening right now. Earlier in 2023, 2024, there was a polymer plant that was actually releasing excessive amounts of benzene into the local community. And it happens to be in a First Nations community. So it really disproportionately affects certain groups, and that's why we were really looking at sustainability and green chemistry as a possible solution to at least not only try to solve the problems, but actually prevent them. So we really were cognizant of these principles. So in 2019, there was a Sustainable Chemistry R&D Act that was signed in the U.S. Congress, which led to this actual report. This is a 72-page report called Sustainable Chemistry Report. It's actually the first thing I read when I started my job at the ACS. So the day I got there, it said, read this and tell me what it's all about. I'm like, okay. So basically, it's a document where the federal government mandated different government departments to make an inventory of all the sustainable chemistry activities that they're currently doing within the federal landscape. And if you look at the amount, it's actually quite significant. In the United States, in the last 4 fiscal years, from 19 to 22, $1.4 billion worth of resources were actually spent on activities related to sustainable chemistry. I have no idea what the amount is in Canada, but that is a lot of money for just sustainable chemistry. And so by having this inventory, they then wanted to see what they can do to identify new innovation areas for chemistry and also where the gaps are in trying to translate these technologies that are developed, let's say, in the federal labs or in academia to industry, because that's really one of the biggest grand challenges right now, is that the lack of translation is really hurting innovation and how these different solutions can be brought to consumers like us. But unfortunately, like any other government department, they also came up with a wall of text. So you can see that if you actually read through the details, it's really basically every alphabet federal agency putting in a little bit of their stuff to make sure that I'm here, I'm here, I'm here. So that's kind of what that is. But shortly after the report came out, we then decided to write an editorial on the report itself. So this little figure actually kind of illustrates that this part of it is the green chemistry part. So these are some of the principles. And these are the parts that are associated on the sustainable chemistry side. So looking at economic and social requirements that are needed for these processes to actually develop materials that become consumer products. You know, the end all of the story is that we need more collaboration, we need more training, and metrics and recognized standards to be able to push the boundaries of sustainable chemistry. So even though there's a new election that just happened, there will be a second part to the report, which is, I think, due this month, actually. So it's coming up. So this is actually where the U.S. will actually lay down the roadmap for what they want to do on sustainable chemistry. And, I'm still Canadian. I'm a Canadian citizen. So anything in the U.S. does is going to affect Canada in one shape or form. And so this is a very important document that's going to be released very soon. It's going to have significant implications on the research directions that the federal government in the United States is going to be pursuing. So, looking at the time, I just want to quickly go through these slides. So, why ACS is involved in this is that in 2022, the board of directors actually created this ACS campaign for a sustainable future, which is really to provide funding to develop activities that can address some of the UN SDGs. We all know that the UN SDGs are currently horribly behind. I think on half of them are terribly behind right now. So this is kind of the ACS's activities towards seeing how we can actually move the bar, even if incrementally, in the right direction towards addressing some of these global challenges. So this started off in 2022, and so every year we have a summit that's devoted to a UN SDG. So in 2022 we had the Zero Hunger one. 2023 was the education one, and if you go to the ACS website, you can actually sign up for the virtual water summit that'll happen on December 11th. What we do is we convene different experts in the field to discuss some of the challenges. There will be panel discussions, which eventually leads to these discovery reports that gets published after the conclusion of these summits. And what I want to say is that moving forward from 2024, we're going to actually move from the virtual summit that we're having here into the national meeting, so having actual discussions in person in San Diego. But to augment some of these summits, we do have grant programs, a sustainability platform, and also some education resources. So this is actually my main job, which is to run a sustainability grant. So we do provide funding for green chemistry and education to the tune of $1 million a year. So this is the thing that I do. And I think that's the important part, is really funding high impact research, but also what can the folks do in the classroom to actually proliferate sustainability, because now with the ACS accredited programs for getting a bachelor's degree in chemistry in the United States, you do need to know green chemistry now. We do have a sustainability platform, so this is done in collaboration with the Center for Green Chemistry and Green Engineering at Yale, and also with Beyond Benign. Check out the website. It's actually quite interesting because it does have a lot of resources on where you can find grants, where you can find publications, who you can actually mentor with. So sign up for that, and you'll actually see a lot of policy information as well. That it's kind of like Wikipedia meets LinkedIn for sustainability. So the little QR codes at the bottom. And then the third thing on the campaign is developing the curriculum. So I think this will be of interest to the professors in the room, but also postdocs that have aspirations for going into lecturing, education. So we do have a number of different free resources available that you can download and utilize to augment your course notes and work with sustainability and green chemistry. They're all completely free, and actually we want you to use them because I think there's the best way to get the word on the street on what this green chemistry and sustainability is all about. In addition to that, we do offer awards and funding for the educators as well. So, moving on to why we're here for today's talk is really the industry programs. And so the ACS Green Chemistry Institute has a number of different industry programs that intersect with different sectors where we convene different companies to actually work together to solve their industry-wide challenges using sustainability and green chemistry in a pre-competitive manner. So these are just some of the photos, and yeah, so that's Izamir. So I work with her all the time on this. So she leads all of these programs. So we do have 3 programs right now. The first one's the Pharmaceutical Roundtable, which I'll talk about in a sec. The Oilfield Chemistry Roundtable is focused on companies that are engaged in sustainability, not at the operator stream, so not at the Chevrons and Exxons of the world, but in the next part when as they're extracting oil out of the ground, how can you be more sustainable? So these companies are interested in looking at safer alternatives for extracting the petrochemical resources out of the ground. And the last one's the Natural Polymers Consortium. So I'll just call it NPC from now on. Just a quick glance on the roundtable for pharma. It's been around for 20 years, so it's been very successful in terms of engaging the international community to work together to solve challenges that they see in the industry using green chemistry. And this is a membership organization, so all the members in this group are actually industry members. And they actually form different working groups to solve things like, what kind of solvent can I use to replace a reaction to make my pharmaceutical? I want to explore flow chemistry. I want to do artificial intelligence for my stuff. So they have like multiple working groups going on right now to actually work together to work in a pre-competitive mode to actually solve these challenges. They themselves will work together, implement those tools and things that they're doing within their organizations. So they do practice what they preach. Whatever they're doing now is actually in making the pharmaceuticals and the APIs that we're currently using. But at the end of the day, working with the GCI, many of these tools and resources are publicly available, and they can actually be beneficial for any scientist right now. So whether you're looking at replacing a solvent with something that's a little bit more benign, these are some of the resources that are available. So these are the roster of the companies. So it's pretty much a who's who of who in the pharma world. So a lot of these companies are interested and passionate about the green chemistry part, and that's kind of the direction that many of these organizations see as meeting their sustainability goals. So why I'm here today is really talk about plastics. So I think we all know that plastics are here and they're never going to go away in our lifetimes. I think that's pretty abundantly clear at this point. But one of the challenges is that with plastics, it's because they're persistent. They're going to stay with us until we're probably long gone. So that's why we really have a lot of challenges right now that need to be addressed with respect to, what are the alternative materials that plastics can be, substituted with, and whether or not the materials that we're going to substitute them with are not regrettable substitutions, because that would compound the problem many times over, not for our generation, but probably 2-3 generations after us. So in 2023, this interesting report came out from the IMF, so that's part of the UN, looking at subsidies for fossil fuel-derived materials. And they did a little calculation and determined that $7 trillion in subsidies are given every year to prop up the petrochemical industry. So yeah, that's a lot of money. And this number, we keep hearing about this 7 trillion any type of meeting I've ever attended in since this report came out. And it was in a DOE meeting, it was in a Change Chemistry meeting. And really the challenge is that with all the subsidies that are going into petrochemical industry, and plus the fact that they have over 100 years of experience taking oil out of the ground and converting it into the products that we use today, it really is a large economic machine that isn't going to go away anytime soon. However, the thought is, what if you can take even a sliver of the 7 trillion and put it into sustainable chemistry, into renewables, into bio-based chemicals? I think there could be a potential impact in that. And so really, it's really getting the industry, the government to really rally around this idea so that it moves the inertia of getting out of petrochemicals into renewable resources. Needs to happen. But that's kind of why the messaging and having these conversations like we are today is important. So with plastics, there was a report in 2017. I think this is from UC Santa Barbara. They did a calculation. How many plastics have been made since the beginning of time? Well, the beginning of time is more or less defined as 1950, so shortly after World War II, as when plastics really started to become prevalent within the consumer markets. And based on their calculation, they said, 8,300 million metric tons of plastics have been made since the beginning of this time period to 2015. But when you look at the graphic here, you'll notice that, most of it doesn't end up being used again. In fact, a small fraction of it is recycled, but the bulk of it is actually discarded or incinerated. And so based on these metrics and their calculations, if by 2017's production in 2050, so where are we now? 26 years from now, we're going to have 12,000 million metric tons of plastic waste in the landfills or the environment if we don't actually do something about it. So, I'm hoping that this number may have gone down a little because, the awareness of plastics pollution, but it's hard to say at this point. What I do want to note from the paper is that one thing that they did try to do was define what plastics is, and it was a very short sentence: synthetic organic polymers. And then much of it were these different plastics that we're all familiar today. So the idea of this plastics definition is actually important, and in the context of the consortium, the NPC itself, is definitions are a key part of the discussion, and how you define something really has an influence on what people perceive it to be and how they want to actually perceive that thing, just like what sustainable chemistry was about. So with microplastics, I think this is probably the problem that most people were familiar with respect to plastic materials itself. So by definition, it's basically anything less than 5 millimeters in size. And there are actually two flavors of microplastics that are currently being made or generated, I should say. So the first one's the primary microplastics. So these are the ones that people actually intentionally manufacture because we want them small in size. So are people familiar back in the day when we had those facial scrubs with the little plastic beads? Yeah, that's kind of thing. So, that's good for exfoliation, but obviously it's bad because there's really no way to get rid of them in a manner that's not environmentally damaging. And to that end, there's been significant legislation against plastic microbeads in the last 10 plus years, starting with the United States. So they banned it in 2015. In Canada, we essentially phased it out by 2018. And even in the EU, they have legislation against not only these things in your facial scrubs, but also in glitter. So it's kind of an interesting definition and a scope of where microplastics is being targeted for phase-out. And one of the things that's actually more interesting from the EU perspective is that they're looking at getting rid of the microplastics in your playground or your soccer pitch now, because those are actually what they have defined as actually the largest source of microplastics pollution right now is actually in artificial turf. So it's kind of a weird thing because now we're not thinking about facial scrubs anymore, but really when we're out in the playgrounds. So the second form of microplastic pollution is really the secondary part of it. So this is the stuff that usually gets tossed in the environment. So it's like your beach or in the ocean, and it degrades or from physical or chemical breakdown. Again, I took something from Canada, so Fisheries and Oceans Canada, and they actually quoted these 4 sources as the main sources of secondary microplastics. So the stuff that we're wearing, so if you're wearing polyester, eventually it degrades and it leaves those residues. Tire dust is another source. Fishing gear is the main one, so there's a lot of fishing industry around the globe, right? And when that equipment, the nets get broken down, they're not going to actually haul it back to land and dispose it properly. This is going to be tossed into the ocean. So that's actually a major source of pollution from that perspective. And then the one that I think we're all familiar with is the single-use plastics. Speaking of this, the garbage in the water, I don't know if anyone's familiar with this whole Great Pacific Garbage Patch. It's like this swirling amount of massive garbage that's kind of going around the ocean right now, moving around based on the ocean currents. And so there's actually 2 pots of this patch right now, and if you actually put them all together in size, it's twice as big as Texas. So, but right now I know you can't actually physically stand on the patch. You know, that would be terrible. But what's really disturbing about this is that, you know, we focus on the Pacific Ocean and its garbage, but in reality, every other ocean right now has its own garbage patch. So it's in the Indian Ocean, it's in the Atlantic Ocean. And so now, you know, this amount of material is really starting to accumulate. And what is its effect on the environment? You know, this is going to be interesting in the next few years. But again, with microplastics, it's even more disturbing when you think about where it ends up being. So it's not just in your, you know, facial scrubs to your artificial playground turf, but now it's actually going to be found in your food sources as well. So in the last few years, there's been significant research actually trying to understand the fate of these microplastics, and are they actually entering within our bodies? And the answer really is yes. So there was a paper in Nature Sustainability that looked at how microplastics are actually being uptake through the crops as it's being grown. That paper in 2020 for fruits and vegetables, it's actually interesting. If you read it, a single apple has more than 100,000 microplastic particles in it. Like a single apple. So think about that. You're actually ingesting, you know, all these different sources just from the fruits and vegetables you buy at Safeway or at Save on Foods. But again, what's more crazy is when you look at where the microplastics are being accumulated in the body, they're actually everywhere now, in your bloodstream, in your brain, reproductive systems, in your bone marrow. You know, these are the kind of things that, you know, we're aware that they're there. The techniques to analyze them are now sophisticated enough that we can detect them. But what is the long-term impact of microplastics within your body? That's still a long story that needs to be investigated by researchers around the world. So to that end, you know, with the single-use plastics that I mentioned, I think what the important part of this is the fact that, you know, we have a lot of legislations against single-use plastics. So in Canada, we've already banned them since well, coming up 2025. And like, actually the funny thing is I went out to eat for dinner and I couldn't finish my dinner. So I wanted a takeout box. I didn't realize you have to pay 50 cents for a box now for takeout. So there's really, you know, things the government is doing to really put the emphasis of not using, you know, single plastics in that sense. And this is actually something similar that's going to kind of happen in California as well. So in 2022, the state of California has signed into law probably one of the most strict laws against single-use plastics. And so, you know, you can see all the different targets that they have for the materials. But one of the things that I would emphasize is that they're actually putting the emphasis of those of the program on the industry itself. So as they're producing the plastics, they're going to actually take the burden of those things and use the $5 billion generated from taking it from the plastics producers to A, cut plastic pollution, so that's good, and B, actually put the money back into programming that would help support environmental justice issues. So this is what's really weird and, you know, unusual is that every jurisdiction has different rules for single-use plastics. So in Canada, we're nationwide, right? But in the States, every state has its own rules. And so how do you unify those kind of activities in a sense that makes sense from a supply chain perspective is actually quite complex for many different companies. So because we have talked about microplastics and, you know, synthetic polymers and they're coming from petrochemical systems, you know, what about natural polymers, which is kind of the topic we're going to talk about today. So the group really that I've been working with is really interested in this field because, you know, they perceive natural polymers as a potential source of polymers that would naturally biodegrade in the environment. So they're not going to be as persistent as plastics. So that's kind of the idea. And so here's another paper. This is from Caltech, and it is Israeli, the Weizmann Institute in Israel. And they actually did a calculation, how much biomass is actually on the planet. And so if you actually read the paper, they say there's actually 500 billion tons of biomass currently right now. Most of it's in plants, and then a small sliver of it's in animals, and then, you know, here we are, this little quadrant down here. What they also did in the calculations determined that most of the biomass is actually on Earth, as opposed to being underground or in the water. But what I want to say is that this number, 500 billion tons of biomass right now, is actually double the amount of the total number of available oil reserves right now that have been identified by the petrochemical industry. So there's clearly way more biomass being made and grown each year than there is oil in the ground right now. And so that itself, you have to think about from the grand scheme of things, is that we do have an opportunity to make use of these resources and make sure that our environmental stewardship is up there. But at the same time, not really have to rely too much on petrochemical resources itself. And this is important because in the United States, bio-based chemicals is actually a big business. It's not small. So more than a little under 4 million people are actually working in the U.S. on things that relate to the bio-based products industry, generating a little under $500 billion worth of revenue. And actually, it's actually an economic driver of one job leads to 2.4 jobs. So this is significant. However, on the grand scheme of things, we all do know that the petrochemical industry is a much bigger, so we're actually adding a couple of zeros to that as well. But it gives you food for thought is that there is potential economic opportunity that the United States sees in looking at bio-based chemicals. So the next two slides, I know I'm not going to get any arguments from anyone on what is a natural polymer, because this group should know and recognize this. But yeah, we do have our lignocellulose, we do have our starch, rubber. We do have the seaweeds, so you can get fucodan and carrageen from green algae and red algae, and also from mushrooms themselves. So, right away there's some sources on the land that we can, and in the water, we can access as natural polymers. Now things get more interesting when we go into the animal side of the house. So we have your chitin from your shrimp and your lobster, so that was my research. But we also think about milk proteins. What about silk, from spiders or from silkworms? Or maybe a little more sophisticated from fermentation within cells producing PHAs. These are some of the sources of natural polymers that we're thinking about that we see in nature and are readily accessible in one shape or form. And we are able to extract these different natural polymers in a couple of ways. So either get them straight from the nature, so from the sources that I showed on the last two slides, or I don't know, is anyone here doing fermentation? Nobody. Interesting. So yeah, we do have fermentation processes that you can actually grow the cells in the lab and then produce them at a scale that you can actually make significant quantities of polymers. So this is just a schematic of PHA. But now, what's really important now is the fact that I want to bring attention to more definitions. So I know there's a lot of that kind of stuff right now. So is anyone familiar with EU REACH? No? Okay. So EU REACH is actually pretty important, and it's going to have implications potentially globally in terms of what they do. It's a law that was signed into effect in 2007. It's registration, evaluation, authorization of chemicals. Really, the gist of it is that you have to register substances if you're making or bringing them into Europe at a amount of 1 metric ton per year. So that isn't much in the grand scheme of things. But when you get into the weeds of why this is important, this becomes important because this is what drives the economy, the global economy. How do you import and export materials, especially from the continental European side? And so this is kind of the slide that is why the NPC came into existence. So in 2012, there was a definition for those natural polymers. So I showed cellulose and milk proteins and stuff. And they identified polymers as result of polymerization processes that take place in nature independently of extraction processes which they have been extracted. So that sounds like number one of where you can get natural polymers. However, a lot of companies and organizations are at odds with that one definition that was written in 2012 because they think that the fate of the particles where the polymerization takes place is non-consequential. So it doesn't matter if you get it from nature or you make it in a test tube. If it's the same polymer, it's going to be the same thing. And the second thing is that if it is the same material, then it should be treated as a natural polymer from the beginning, irregardless of different exemptions. So really, there's kind of a science question to this, And then there's the economic question to this. And a lot of companies are really against this definition because there's actually possible consequences. So it may not be apparent right now because we're all doing our research in the laboratories, but if something like this gets set as a precedent, it could lead to different laws being developed based on a definition that isn't scientifically correct. So that's what some organizations think. Another one is that this creates an unnecessary barrier to innovation for bioproducts, because why would a company get involved in developing biomaterials if there's going to be significant legal barriers to get their stuff to market? So they're already aware of that problem. And the last thing is more of a social economic argument, is that, okay, if we don't do anything that's innovative in this space, we're going to start losing jobs in the bioeconomy, and we're going to continue to use petrochemicals. So this one slide is kind of the essence of why this group formed, which is the Natural Polymers Consortium. So we actually have been talking about it since 2022. Some initial discussions with the different national meetings. Eventually, the band formed in Denver in 2024, and our founding members include Colgate, Procter & Gamble, International Flavors and Fragrance, Monosol, and Rocky Tech, a small medium enterprise. One of the reasons why this group came together is the fact that they actually belong to different supply chains. They're in different parts of where they are on the value chain itself, but they all want to look at the development of natural polymers and look at how they can actually become scalable and also commercializable into consumer products. So that's kind of our vision. We want to meet modern human needs, but the mission is actually the more important part, is to actually look at those different innovations from development, production, applications, and to actually be able to use natural polymers in consumer products. But the group is also interested in looking at using foundational science. So not application science, but foundational science to actually drive the acceptance of these materials through policy and regulatory processes. So there's really a big core difference with this group, is the fact that they definitely embrace the science. They think it's important. We need to understand the fundamentals of what natural polymers can and can't do. But at the same time, recognizing that you need to be able to actually back up your claims, and bring that to the lawmakers that are able to actually, drive regulations that allow for your products to come to market. So, this kind of summarizes what I said before, but, they are definitely interested in looking at the plastics problem. They are looking at addressing industry-wide bottlenecks, just like the Pharmaceutical Roundtable. So they're going to identify challenges that their industries are facing, and whether or not working with industry groups, academic groups, governments to be able to solve these challenges. And at the same time, really working together, but maintaining their individual competitive advantages as corporations. So really there's a balancing act of doing the research together, but at the same time doing it in such a way that they don't lose market share of their own products. So I got 2 more slides left. So these are kind of the strategic priorities. So the first one's really bringing the communication. So that's why I'm here today, is that bringing the word of that the Natural Polymers Consortium is real. We're willing and want to work with groups like the UBC to really look at what are those challenges that even you are facing right now in trying to get traction of bioproducts to from translation of in the lab to where it needs to be on the industry side. Promoting research, so this is kind of where we're looking at possible funding, developing the metrics and tools. I think that's the important part, because a lot of the magic of the science really happens in academia. So, but we need to develop associated tools and technologies that make sense, that allows us to really characterize and analyze what these natural polymers are. And lastly, once we kind of have all this information, we need to advocate for this recognition. So bringing it to the attention of the government, policymakers, and even NGOs that may recognize the need that, okay, we have a natural polymer that's actually potentially good, but is it really good for our communities if it's implemented? So we need to have those conversations as well with the folks like that. Now, this is a slide that I kind of paraphrased. It was actually from a guy from McKinsey that kind of brought it up, and I actually like it because every time we actually try to address technologies, we always emphasize on fixing the negatives. So these are kind of the big five we always see right now in terms of the negatives. So greenhouse gases, so contributes to climate change. Resource depletion, we're running out of petrochemicals. Toxicity, what happens when these microplastics or other materials are in our bodies or within our environment. End of life, how long does this stuff actually persist in the environment? Is it going to affect generations to come? And then that's the ocean pollution, so the mounds of garbage in all the oceans right now. However, we don't actually emphasize a lot too much on positive challenges, and this is kind of where we want to change the thinking a little bit. How do we actually improve human health and the environment through the innovations that everyone here is developing here at UBC? I think that's kind of the one thing that we never prop up about, because we always talk about the negatives. And then the second part, which is of course of interest to industry, is like, how do you get these materials to market so that they actually get to the value chain to reach their sustainability goals? So there's that societal requirement and there's that economic requirement. And I think I kind of want to emphasize the positives here of these challenges, because these are the things that actually matter the most. These things we'll have to solve as we fix these problems. So that just comes back to the sustainability chemistry thing I showed earlier, using green chemistry as those tools to actually address some of those economic and social requirements that are put onto us. So really what I want to put on this slide, because I want to leave time for questions, is the fact that we have different areas that fit within these strategic priorities. So if we just stick with the science part, we're definitely looking at replacing synthetic polymers, getting better performance out of them, because no one's going to buy anything that's worse performing than what you already have right now. So this leads to really that whole concept of structure-function relationship. How do we formulate a product? And then how do we actually make these products without the trade-offs that are associated with the incumbent materials? But from a holistic life cycle analysis and systems thinking approach, we need to think about all four of these boxes to be able to come to the solutions that we're looking for. So in my last slide here, which I'll leave up, how can you work with the NPC? So we do have two co-chairs, Jun Wang and Matt Wagner from Colgate and P&G. They're the ones leading our stakeholder engagement. We're currently writing a position paper right now to really define what this group wants to say about natural polymers. We're not going to define natural polymers, but the group wants to really look at what is the scope of what natural polymer is right now, what needs to be done to get to scale and to get to market, while meeting the social and the economic requirements that are currently existent today. So to that end, we'll have symposium webinars. So just a little plug for our conference. This is going to be in Pittsburgh, the Green Chemistry and Engineering Conference. We're going to definitely have a whole day session on natural polymers. So we're going to have a lot of industry folks, a lot of, hopefully some of you might attend to participate in this discussion. And lastly, this is not a single technical division, as what Scott has said. It really is driving different groups from around the ACS community, different multidisciplinary research areas to solve the challenges. So it's not just a polymer group. We need cellulose, we need carbohydrate, we need inorganic chemists, we need analytical chemists to actually, figure out how we can actually get natural polymers to the way things are with petrochemical research right now. So I'll leave it at that right now, but if you have any questions, you can check out the dinosaur QR code that leads to the webpage, and you can contact myself or Izamir, but I want to thank you for your time, and I'm happy to take any questions. Thank you.